So when we purchase hydrochloric acid, we actually buy a giant container of hydrochloric acid that is extremely concentrated. It actually is 12 moles per liter, 12 molarity. Now, this is just for shipping purposes, so that they can send us very concentrated acid, and then what we can do is actually water it down to get it to the concentration that we want. Now, 12 moles per liter is quite concentrated. It's very, very dangerous in this situation, but it's easier to ship it when it's more concentrated like this, because you're shipping more in a smaller bottle. Now, what happens when you actually dilute it, when you water it down? You actually have the stock solution, which has the hydrochloric acid dissolved in the water, but then after you add water to it, it's watered down. You still have the same amount of hydrochloric acid in there, the same number of moles of hydrochloric acid in there. That hasn't changed, but now you have more solution, so it's actually more spread out here. Now, there's a way to calculate this. So going back to this problem here. Let's say I have an experiment that requires 435 milliliters of a 2.0 molarity hydrochloric acid. So that's what I want. I need this much, and that's the concentration I need. Now, the bottle is 12 molarity. So how much of that 12 molarity do I put into the beaker before I add water and water it down? That's the question. How much do I need? Well, there's a formula for this. It's actually M1 times V1 equals M2 times V2. M stands for the concentration, the molarity. V stands for the volume, how much I actually need. So let me show you how this works. Okay, so my container of hydrochloric acid, its concentration is 12 moles per liter. This is actually the concentration I'm starting with, so this is M1. All right, now in a given experiment, it requires 435 milliliters. This 435 milliliters, this is actually V2. That is the concentration that I'm looking for. All right, and then, excuse me, the volume that I'm looking for. The concentration that I'm looking for is 2.0 molarity, so this is actually M2. And then it wants to know how much of the 12 molar HCl is needed, so that is actually V1. So it's giving us what we're looking for, M2 and V2. We're starting with this concentration, M1, and we're looking for how much of that M1 we need. So we're just going to take all these numbers and plug them into the formula here. M1 is 12 molarity. V1 is, we don't know, so that's what we're looking for, so I'm going to leave that as a variable. Then M2 is 2.0 molarity times V2, which is 435 molarity. All right, so put everything in there, figure out what it is, and put it in there. And then we're looking for V1 here. So I'm actually going to try and get this all by itself. So I'm going to divide both sides by 12 molarity, so it cancels on this side. Divide this side by 12 molarity as well. Now I'm just going to take this and plug into a calculator. The only thing left on this side is V1, so whatever this is my answer. So let me grab a calculator here. We have 2.0 times 435 divided by 12. Answer is 72.5. Now, before I write this down, I'm going to look at significant figures here. So this one has two significant figures. This one's got 3. This one has 2 significant figures. So 2 is what I have for lowest here. So my answer has to have 2. So this would round up to 73 milliliters. Now, you may have noticed that it gave me a volume in milliliters up here, 435 milliliters. I did not convert that to liters. I don't have to convert it to liters to actually do this problem. But my answer will be in the same units. So if I do convert this to liters, that's okay. But then your answer will be in liters. You wouldn't get 73 milliliters, you would get 0.073 liters. Okay, so let's do a second problem here, second example. So this new problem, if I have 31.5 milliliters of a 2.5 molarity solution of sodium hydroxide, NaOH, it's diluted to 525 milliliters of the solution, what would the new concentration of the solution be? So once again, formula, M1V1 equals M2V2. I'm going to identify all the pieces here. So I'm starting with a concentrated solution of sodium hydroxide, and I know its concentration and I know how much. So this right here, this is V1, sorry. This is M1. Okay, it's starting concentration and its starting volume. This right here is V2, so that's what I'm diluting it down to. It's asking about the new concentration, so it's asking about M2. That's the thing we don't know. So I'm going to plug these numbers in. 31.5 milliliters here. Again, I don't have to change that into liters because I've actually got milliliters on both sides, so they're just going to cancel. Times the starting concentration is 2.5 molarity is equal to the concentration that it's new. I don't know that, so I'm just going to leave that as M2. And the volume that I'm changing it to is 525 milliliters. Okay, I want to isolate M2, the new concentration, so I'm going to divide this side by 525 milliliters, so it cancels. And then divide this side by that as well, 525 milliliters. So the only thing left on this side is my new concentration, M2. This I can plug into a calculator, and as you can see, the milliliters are being divided by milliliters, so that's actually canceling it out. As long as you don't convert them, they cancel out because they were both milliliters. Okay, so plug this in here. 31.5 times 2.5, 0 divided by 525 is 0.15. Now, before I write it down, sig figs. This has 3, this has 3, and this has 3, so my answer gets 3 sig figs. This answer on the calculator only has 2, so I actually have to add a sig fig to this. So what I'm going to do is not write 0.15, I'm going to write 0.150, an extra sig fig there, molarity. And that is my new concentration.